Welcome to this video. It's on the initial rates method, which is used to work out the orders of a reaction. The specification reference for this lesson is 3.4.1. So whereas before we started with a rate equation and used it to work out things like the rate constant given various concentrations and rates, what we'll do now is actually derive the rate equation in the first place for a reaction from data relating the initial rate to the concentrations of different reactants. Let's first just be clear about what we mean about the initial rate. Now, the initial rate is the rate at the very start of the reaction, when you first mix the reactants together. And that's useful because at that point, right at the start of the reaction, we know the starting concentrations of the reactants. That's why the initial rate is used. So to find the initial rate of a reaction, we have to create a chemical reaction. And we might create a chemical reaction such as one that creates gas. We collect the gas and measure the amount of gas produced over time. Or we might look at a reaction that involves a color change, and we could measure the color change over time. And we do that because we'd want to draw a concentration versus time chart. So let's just draw one of those. So on the y-axis, you would want the concentration of the reactant. Let's call the reactant A, all right, and the concentration of that. And we want to see how that changes with time. Now, at the start, the concentration of A is going to be the highest because none of it has reacted yet. And as the reaction proceeds, it's going to decrease. But it's going to decrease at a decreasing rate, all right, because the rate of the reaction changes. And unless it's an equilibrium reaction, it will eventually get to zero when the reaction is finished. So we have a curve there showing the change in concentration over time. And what we want to do is we want to find the reaction rate at the start of the reaction. So we draw our tangent from this point here, and so the tangent might look like that. That's poorly drawn, but I think you get the idea. And then we would take the gradient of this tangent, where let's call this delta y, and let's call this delta x. And so the initial rate is going to be the gradient of that tangent at the initial conditions. So it's going to be delta y over delta x. And that is the initial rate of this reaction. Then what we might do is we might use different concentrations to get different rates and work out then the relationship between concentration change and how that changes the rate. That's what we're going to do next. So this is the method of the initial rates method. And what we're going to do first is we're going to set up the reaction, as we said, and we're going to monitor the amount of reactant or product over time so that we can draw one of those concentration time charts. And then we're going to repeat the experiment several times. But each time we will use a different initial concentration of one of the reactants. And note that everything else needs to stay constant, because what we want to do is we want to look at the change in an initial concentration of one of the reactants and see what happens to the rate. And then we can do the same for the other reactants. After that, we will be able to calculate the initial rate for each experiment by taking a tangent, as we've done on the previous slide. And once we've got all the reaction rates, we can then compare what's happened to those rates. Have they increased? Have they decreased? As we have increased or decreased the initial concentrations of each reactant. And that will allow us to figure out the order with respect to each reactant. So let's consider this reaction here between nitrogen monoxide and chlorine to make nitrogen oxychloride. Two reactants being nitrogen monoxide and chlorine. And so what we would do is we would run some experiments varying the concentrations of nitrogen monoxide and chlorine. So we might do 3 experiments. For example, one might take the concentration of nitrogen monoxide, right, and measure that over time, and it might start out at let's say 2 moles per decimeter cubed, right, and that might have a concentration time curve such as that, in which case we would take our tangent at the initial conditions and work out the gradient. So the initial rate let's call it initial rate 1 would be y1 over x1. Then we might do a second experiment, and we might in this time also look at the concentration of nitrogen monoxide over time. But in this case, we might start with a 1 mole per decimeter cubed concentration, in which case we might get a concentration time chart like that. And then we would take the gradient here, take the tangent rather, and work out the gradient of that tangent. So let's call that y2 and x2. So the initial rate of this experiment, let's call that initial rate 2, might be, well, it would be y2 over x2. Now we've got one initial rate for these starting conditions here, and another initial rate in the first experiment starting from a higher concentration of nitrogen monoxide. That might well allow us to work out the order of reaction with respect to nitrogen monoxide, but in order to get the order of the reaction with respect to chlorine, we might want to do a third reaction. And in this case, let's then, in a very similar way, do another concentration time chart. But in this case, you would start with a chlorine concentration and look at that over time. And you might start with 2, and you might get a concentration time chart like that. Take your tangent at time equals 0. Work out the gradient. So the initial rate, number 3, would be y3 over x3 again. Okay, and if you choose your concentrations carefully, then with just 3 experiments in this case, you would get all the data on initial rates and concentrations that you would need to work out the orders of reaction with respect to both nitrogen monoxide and chlorine. We're going to have a look at that now in tabular form to make that crystal clear. Okay, so here we have a results table from 3 experiments that we've done with this reaction. And may I draw your attention to experiments 1 and 2. So you'll see in experiments 1 and 2 that what we were trying to do is we were trying to work out first the order of the reaction with respect to nitrogen monoxide. So what we had to do is we had to keep the concentration of chlorine the same, so it would be a fair test. And what we did with these 2 experiments is we did the first one at a concentration of 0.125 mole per decimeter cubed and worked out the initial rate for that starting concentration. And then we did the second experiment at 0.25 moles per decimeter cubed, which is twice as much. Okay, so you can see what we've done is we have doubled the starting concentration of nitrogen monoxide while keeping the concentration of chlorine the same. So when we do that, we look at what's happened to the initial rate. So when the starting concentration of nitrogen monoxide was 0.125, the initial rate was 1.79 times 10 to the minus 7. And then when we doubled the concentration to 0.25 moles per decimeter cubed, the initial rate went right up to 7.16 times 10 to the minus 17. And so we can look at the ratio there, and what we can see is that the initial rate has increased by 4 times. So we've doubled the concentration, increased the concentration by 2 times, yet the rate increases by 4 times. So if you imagine a rate equation, the rate is going to be, in this case, it's in relative terms, the rate has gone from 1 to 4. All right, so 4 is going to be equal to the concentration of nitrogen monoxide, which has gone from 1 to 2, all right, to a power, to the order of the reaction with respect to nitrogen monoxide. So we can see that that has to be 2 squared. 4 equals 2 squared, where this is the order of the reaction with respect to nitrogen monoxide. And this is what happened to the rate, and this is what happened to the concentration. And so now we know that the order of the reaction with respect to nitrogen monoxide is 2. And that we got from experiments 1 and 2. And when we were doing this series of experiments, we chose the concentrations very carefully, such that we can use now experiments 2 and 3 to do the same for chlorine. So if you notice, in experiments 2 and 3, this time we are trying to work out the order of the reaction with respect to chlorine. So we need to keep the initial concentrations of nitrogen monoxide the same. So they've been kept the same at 0.25 moles per decimeter cubed. And instead what we've done is we've changed the concentration of chlorine. All right, so we started off in experiment 2 with a concentration of 0.125, and we got from that an initial rate of 7.16 times 10 to the minus 7. So we look at what's happened with the change with the concentration. What we have done is we have doubled that concentration in the third experiment. So that has gone from 0.125 to 0.250. That's a doubling of the concentration. And you can see from here the effect that that doubling of concentration has had on the initial rate. And the initial rate has gone from 7.16 to 1.43 times 10 to the minus 6. And when you divide one by the other, you can quite quickly see that it's also doubling. So in the same way as we did for nitrogen monoxide, let's see what that tells us about the order of the reaction. So the rate has gone from 1 to 2. All right, and so that is equal to the concentration to the power, which is the order of the reaction with respect to chlorine. So the concentration has also gone from 1 to 2, and clearly 2 equals 2 to the power of 1. All right, so in the same way, what we've worked out is that 1 is the order of reaction with respect to chlorine. And just for the sake of completeness, this was what happened to the rate when we changed the concentration. So doubled the concentration and doubled the rate, so the order of the reaction with respect to chlorine must be 1. Now, the question, of course, is asking us to write down the rate equation for the reaction. And so we can write that down now, as the rate is equal to K times the concentration of nitrogen monoxide. We've worked out the order to be 2, and times the concentration of chlorine. We've worked that order to be 1, and so the rate equation for this reaction is there. So we've got another example here, a slightly more complicated example because we have 3 reactants. And we've got nitrogen monoxide reacting with carbon monoxide and oxygen gas to give us nitrogen dioxide and carbon dioxide. And we've done 4 initial rate experiments at various concentrations of those 3 reactants, working out the initial rate for each of those combinations of reactant concentrations in order to work out the orders of reaction with respect to all 3 individual reactants. Okay, so let's start off by trying to work out the order of the reaction with respect to nitrogen monoxide. So what we would like is for the other concentrations, the other reactants concentrations, to be the same. And so we can see that in experiments 1 and 2, we have the same concentrations of carbon monoxide, and we also have the same concentrations of oxygen. So that means that any difference in the initial rate is down to the change we make to the concentration of nitrogen monoxide. So let's look at the concentration change that we make. We start off with 2 times 10 to the minus 2, and then the second one we do 6.0 times 10 to the minus 2, which of course is a tripling of the concentration. So that tripling of the concentration, let's see what effect it has on the initial rate. And you can see that the initial rate goes from 0.17 to 1.53 moles per decimeter cubed per second. And when you look at that one divided by the other, you can see that that is times 9. Okay, so if down here we work out the order with respect to nitrogen monoxide, we do that by saying that the rate has increased by a factor of 9 when the concentration has increased by a factor of 3. So for 9 to be equal to 3, it needs to be to the power of 2. Okay, so we have 2 as the order with respect to nitrogen monoxide. So there we have the first order of the first reactant. Okay, so let's now have a look and see if we can find out the order of the reaction with respect to carbon monoxide. So what we would like is we would like the other concentrations to be the same. So if we look then at experiments 1 and 3, you can see that the concentrations of nitrogen monoxide are 2 and 2, they're the same, and you can see that the concentrations of oxygen are 1 and 1, they're the same. So that means that any change in the initial rate is down just to the change in concentration of carbon monoxide. So we can see that in experiment 1, we started off with 1 and we changed that to 2, which is a doubling of the concentration. But when we did that, look what happened to the rate. The rate didn't change. The rate stayed as 0.17 moles per dm cubed per second. So that means we can calculate the order of the reaction with respect to carbon monoxide. So carbon monoxide is given by the factor of increase in the rate, right, which was 1, it stayed the same, and that equals the factor of increase in the concentration, which was 2. Right, so for 1 to equal 2, it needs to be the power of 0. Okay, so 0 is the order with respect to carbon monoxide. Done. So now let's have a look at oxygen. Okay, so what we're going to do is, what we would really like to do is, we would really like the concentrations of nitrogen monoxide and carbon monoxide to be the same, but I don't think we have that data. Right, so that's where this gets slightly more complicated. So if we had a look at experiments 1 and 4, you would see that, let's draw our line here, you would see that the concentration of carbon monoxide is the same. However, the concentration of nitrogen oxide goes from 2 to 4. Okay, so first thing we need to do before we look at the effect that the change in concentration of oxygen will have on the rate is we have to work out what the change in concentration of nitrogen monoxide has on that rate. Now we have doubled the concentration of nitrogen monoxide from 2 to 4, and so you would expect that to quadruple the rate. Okay, so if nitrogen monoxide was the only thing that was affecting the rate would increase from 0.17 to 4 times 0.17, which is in fact 0.68. So what we can see then is that all of the increase in initial reaction rate is down to nitrogen monoxide. So what you can see is that when you increase the concentration of oxygen from 1 to 2, we've doubled that. We have not increased the initial rate by any more than the increase in rate that's down to the nitrogen monoxide. So if I put it like that. So now we can work out the order of the reaction with respect to oxygen. I think you've probably guessed already. Okay, so we have the increase in rate was a factor of 1, and 1 equals the increase in concentration of oxygen, which was doubled, so the factor was 2, and so 2 has to be to the power of 0, all right, for it to be equal to 1. So 0 is the order with respect to oxygen. So now we have the 3 orders of the 3 reactants. So we can write down now the rate equation, which is what we're being asked for. Okay, so at the bottom down here in black, I'm going to say rate equals the rate constant, right, times the concentration of nitrogen monoxide, because nitrogen monoxide changes do affect the rate, and we've worked out the order to be 2. And that's it, because carbon monoxide is to the order of 0, so we don't include that in the rate equation, and oxygen is of 0 order, so we don't include that in the rate equation either. So the rate equation for this reaction is there. So finally, let's just check that we've met our learning objective. We set out to be able to derive the rate equation for a reaction from data relating initial rates to the concentrations of different reactants. And we've done that for a 2-reactant reaction and also for a 3-reactant reaction. See you in the next video.